Question 7 then gives us a ring on a curtain pole. Ring weighs 0.3 G newtons. We have a normal contact force N. The string pulling it in this direction, there's a tension of 2.5, and because it's moving to the left, then my frictional force must be acting to the right. If it's in limiting equilibrium, it's just about to move, which means that friction is at its maximum. So again, the first thing I need to do is resolve my forces here. So if this angle is alpha, it's adjacent to this component, so this is 2.5 cos alpha, which means this one here is 2.5 sine alpha. I'm also told that tan of alpha is 3/4. So I've drawn myself a little triangle, a little right angle triangle, marked alpha in as one of the angles, and tan is opposite over adjacent. And if I then use Pythagoras to work out the hypotenuse, this must be 5. So from here I can say that sine alpha is 3/5, and then cos alpha is 4/5. And I don't know what mu is, that's what I'm trying to find. So if we have a look at part A, first thing I'm going to do is resolve my forces in a vertical direction. So if I look at N going up, and I've got 0.3 G plus 2.5 sine alpha coming down. So N is going to be 0.3 times 9.8 plus 2.5 times, now the sine of alpha is 3/5, so times 0.6, so N comes out to be 4.44 newtons. I'm then going to resolve my forces horizontally. So friction heading off to the left is 2.5 cos alpha. So my friction is 2.5 times the cos of alpha. Now cos alpha is 4/5, so 0.8. So friction is equal to 2. And then finally I'm going to use F equals mu N. So 2 is equal to mu times 4.44, which tells us that mu is going to be 0.450 to 3 significant figures if you like. Okay, so part B asks me to find the normal reaction now that my string force is coming up rather than pointing down. Because of the change in the direction of the string, then the normal contact force is different. It's different to what it was in the first one. So I've called it R this time and just drawn the diagram again. So what I need to do in this case is resolve my forces vertically. So R plus 2.5 sine alpha going up is equal to 0.3 G coming down. So R is going to be 0.3 times 9.8, take away 2.5 times the sine of alpha, and the sine of alpha again from the triangle above is 0.6, and this comes out to be 1.44 newtons. Part C then is asking if the ring is in equilibrium. So in order to do this, we need to consider the forces acting along the pole. So friction we worked out in part A, and friction is equal to 2 newtons. And the component of the tension as acting towards the right is 2.5 cos alpha, and this comes out to be 1.44. Now if this is going to move, then this value here needs to be bigger than the frictional force. 1.44 is clearly less than frictional force, so 1.44 newtons is less than 2 newtons, yeah, therefore no movement. Yeah, friction has not reached its maximum value, which is 2. It only needs to be 1.44 to stop motion occurring. Therefore, it's not in equilibrium.